In the last section of this unit, we're going to explore uh, something called trigonometric identities. In some ways, it's related to trigonometry because we're going to deal with sine, cosine, and tangent, and also the reciprocal trig ratios of cosecant, secant, and cotangent. But in other ways, it's very different, and in fact, doesn't really apply the trigonometry that we've done for the rest of the unit. I really love this part of this unit because I see trig identities as sort of like a puzzle that needs to be solved. I'm looking for one piece, one small step that I could get closer to the solution. In some ways, it's the most challenging, and this is why maybe it's frustration for a lot of students, but hopefully we will have some fun with it. So how I'd like to introduce trig identities is just with a simple word puzzle. And here, my theory is that math can be a ball if we have the right attitude and we follow the right steps. So this puzzle is that we want to convert math to ball, and the rules are that we can only change one letter at a time to form a new word, and that word that we form must be valid. Okay, so I mean, we could just jump to say, well, we're going to change the H to an L, and that's how we get closer from math to ball. Doesn't quite work because MATL is not a valid word. So if you haven't done this yet, I just encourage you to pause the video and give it a shot. So as we go from math to ball, there's some steps that are going in there that he says, not sure how I may be able to handle that. So one thing that we could do as a strategy is to go straight down and work directly in that way. But sometimes it might be easier to see a solution working from the from the bottom up. So one way that I see a solution for this is, well, we know the A is not going to change. And maybe I could change the B, or sorry, M to a B, but I'm actually seeing going up this way, and I'm changing the B to an M. So here I actually got one intermediate step of a mall. So now I'm really trying to get from math to mall. So I could replace this L with a T, but that's not going to be a word. I could replace this L with an H, but that's not going to be a word. So really I need an intermediate step here that maybe doesn't make sense, but in some ways it does get us closer. So one thing that I'm going to say is that I'm going to see that I can convert mall to male. So here the L turns into an E. It seems like that's a useless step because it doesn't get anywhere closer. But what that allows me to do is actually change the L to a T. So I get mate. And then finally from mate to math. So here I actually worked from bottom to top. You could have come up, there's many different solutions. I mean, if I saw this coming along down here, I could have came up with going from math to mate. That one was a little bit more difficult to see because here E is not in the final word. So just recognizing it's an intermediate step. So trig identity, when we go off and prove trig identities, is really something very similar. And the thing I love about trig identities is we are given some ways the solution. We're given the final thing that we're looking for. We're given the start and the final thing. So here we have those two ends, and we're just seeing, well, what's one step that gets me closer to the final destination or the final target, or in this case, the final identity. So here's our success criteria. We're going to understand and define what an identity is. But more importantly, really the whole heart of this section is we're going to prove trigonometric identities using defined trigonometric definitions. So in this case, sine, cosine, and tangent. Remember, those are definitions, as well as cosecant, secant, and cotangent, and other identities that we will prove as well. So that's one thing about trig identities is once you prove an identity, once we've shown that this is true, we could use that identity for other proofs. Now, some of the identities that we're going to prove are so weird looking that chances are of you reusing that identity for another proof is rare. Okay, but there's a couple that we'll do right at the beginning that's really fundamental to how we will prove future or other identities as we go through this section. So first, let's define an identity. Identity is an equation that is always true for all possible values of its variables. Identities that involve trig functions are called trigonometric identities. To prove that you have an identity, you must start from one side, in other words, one side of the equal sign, then work all the way to the other side to show that the left side is eventually equal to the right side. Okay? So here we have some identities to start with. I mean, they're really definitions, but we're going to call them the reciprocal identities. And really, we see that the cosecant is 1 over sine of theta by definition. Also, secant is 1 over cos of theta, and cotangent is 1 over tangent. So one of the first proofs that we're going to do is that tan of theta is really sine of theta over cos of theta. What we're saying by this identity is that no matter what angle we choose, that's what theta is for, no matter what value we choose, we're going to say that when we plug in a tan of theta, we get a certain value, but when we do sine of theta over cos of theta, we're going to get that exact value. Now, a proof is not plugging in numbers. For example, I'm not going to prove this by using theta for 1, so I'm going to plug in the calculator tan of 1, get a certain value, and then in the calculator also plug in sine of 1 divided by cos of 1, and we're going to see get the exact same value. We can't use that as a proof because there's no possible way that we could go through every single possible angle, because there's an infinite amount, to say that this is true. Even though here it says that, well, theta is between 0 and 360 degrees, well, in reality, theta is a real number, so there's decimals involved in there, so we can't go off and plug in every single possible real number. So this is what a proof looks like. So we need to start with the left side and the right side. So when you do your proofs, this is my expectation. You break it up into left side and right side. So the first thing I do is just copy down really the left side of the equation and the right side of the equation. So for this one, it's actually going to be easier to start from the right side. Normally, depending on what your trig identity looks like, it might be easier to start from the left. But in this one is actually easier to start from the right because we know some of the definitions in here. So notice that we can't sort of cross this border here. And thus we can't apply algebra. It's not like an equation where we're going to apply algebra to one side and also apply to the other. We can only work on one side and one side only, and we can only sort of take one logical step from one to another. So in this case, I'm just going to write down the definitions of sine of theta and cos of theta. So sine of theta by definition is y over r, and cos of theta is x over r. Then, because we're divided by a fraction, we're just going to multiply by the reciprocal, so we get y over r times r over x. And so what we discover is that, well, the r's can reduce or cancel out, and we get y over x. But this is the definition of tan of theta. So this is one example of how how something is proven. So at the end of the proof, once we get left side is equal to right side, I do a square, a cube or a square. I shade it in, and I write the words QED for, it's Latin for something like, and so it is. I'm sure that the word for word, that's not what it means, but essentially that's saying that this is proven. So this one is called a quotient identity. I don't know why it's called a quotient identity, but basically because we're saying that tan is really sine over cos of theta. So here's another one that will be used often. Both of these will be used often. So the idea is that now that we've proven that tan of theta is equal to sine over cos of theta, anywhere in our trig identities that we see tan of theta, we could just substitute sine of theta over cos of theta now, which is really the very first step of all trig identities. So I'll give you some hints as we go through this, is you want to replace all tans with sine over cos. So here's one thing. Replace all tan of thetas with sine over cos. Okay, so here's an identity where we're going to prove that sine square theta plus cos square theta is equal to 1. So this is actually really interesting. So we're saying that for any angle, if you take sine of it, so that's one thing about notation here I want to talk about, is that this is sine square theta. So this is really saying sine of theta times sine of theta. Okay, which is very different than if we had something like sine theta squared, because there the square is on the angle. So in other words, we would square the angle first and take the sine. So mathematicians are lazy. How can we sort of shortcut and write sine of theta times sine of theta? So what they did is they put the exponent next to the trig ratio as opposed to the theta, the angle. So here we got sine square theta, and over sine of theta times sine of theta plus cos square theta. And no matter what angle we put in, if we do that in a calculator, the answer will always be 1. So here we're actually going to prove that. So again, we're going to do left side and right side. So the right side is simple, and I could tell you that we're not going to touch the right side. We're going to work from everything from the left side. So we get sine square theta plus cos square theta. So let's go back to the definition. So sine square theta is y over r, quantity squared. And cos square theta is x over r, quantity squared. All right? Then we're just going to expand that. So here we get y squared over r squared plus x squared over r squared. So here's another hint for identities, and I've given this as well when we did rational expressions, is whenever we have two fractions, we can always add them together. And most of the time we discover when we have trig identities, and you can kind of see that one side has a fraction, the other side doesn't have a fraction, we know we're going to have to add these fractions together. In this case, it's possible because they have a common denominator, so we don't have to do anything with this. So this is really x squared plus y squared over r squared. But in the last section where we talked about a point, we'll have a point x comma y, and this could be anywhere in our Cartesian plane. So there's our radius. It goes from the origin to our point. Well, we call it, this was r, remember, that was the radius of the circle that would be formed. Well, how do we actually calculate r? We said that r squared is equal to x squared plus y squared. In other words, we use the Pythagoras theorem. So here, using the Pythagoras theorem, knowing that when we have a point in our Cartesian plane, the x squared is equal to x squared plus y squared is equal to r squared, we could actually replace x squared plus y squared with r squared. And notice that when we get r squared over r squared, well, that simplifies to just 1. And so that is that proof. Okay, so it's kind of cool. So this one in particular is called the Pythagorean identity, because it's based off of the Pythagoras theorem. But really, this is going to be something that we're going to use often again. And as we go off and prove trig identities, actually that's one of the things that we're going to look for. And you can almost kind of see, well, one side has sine and cos, and this one, they're kind of gone. Is that we want to get that sort of magic combination of sine squared plus cos squared, and that actually really simplifies to 1. Okay, and we'll go through a couple examples where we can kind of see that within an equation. So while we have this identity, sine squared plus cos squared is equal to 1, we actually have two what we call corollaries off of that identity. So basically, we can isolate for sine squared. So we can say that sine squared theta is actually 1 minus cos squared theta. So sometimes that might be handy in one of our proofs. And likewise, we could say that cos squared theta is equal to 1 minus sine squared theta. So where we might see this handy in the proof is that one side we see cos, the other side we only see sine. Well, is there a relationship between sine and cos where basically one converts to another? We want to say that. Well, here's a hint to maybe an identity that we can use in order to sort of get from sine to cos and vice versa. I'm going to stop here too and also say that this is probably the last two identities that we'll prove by actually going back to the definitions of sine and cosine and tangent. In other words, using x, y's, and r's. From here on in, the rest of all these proofs will just deal with the trig ratios of sine, cosine, tangent. They'll be in there, and we just work directly with them. Now, notice that um, this is why these two identities are so important, because this is how we really get from one trig ratio to another. In other words, how do we get from tan to something with sine and cosine? Well, we use the quotient identity. And likewise, if we have something that's sine in the other side, or the side of cosine has to do with cos, well, how do we sort of convert a sine to a cos? Well, here's we're using the Pythagorean identity. So let's look at one. So there's several proofs. So the thing about proofs is that there's just techniques that you learn and you apply, and hopefully every single identity is going to be different. So that's why identities are tough. It's not a single process that you might follow. So for example, figuring out the sine of an angle between 0 and 360. So we have a definite process for that. Not so much with proofs. Okay, so really practicing is really a great way to get better at proofs, seeing proofs. So as we go through there, so I'm going to show you various proofs that we're going to do. And with each of the proofs, hopefully we can see a trick, if we want to call it a trick. But there's something that maybe we could do within that identity to prove it. So in this case, we're going to prove that sine of theta over tan of theta is equal to cos of theta. So again, we have left-hand side, right-hand side. Okay. So again, we just copy it down. So left-hand side is sine of theta over tan of theta, and the right-hand side is going to be cos of theta. So being that the left side is a little bit more complicated, that's probably what we're going to start off with, because we could sort of simplify it with each step. So here, again, one of the first steps I said was always replace tan of theta with sine and cos. Notice that on this side, there is no tan. So here we sort of want to get rid of the tan, and we know that we have the quotient identity. So we know that that this is going to be sine of theta over, so tan of theta was sine of theta over cos of theta. So here we're dividing by a fraction, so we'll multiply by the reciprocal. So that's going to be sine of theta times cos of theta over sine of theta. Well, in this case, the sine of thetas cancel out, and we're just left with cos of theta. So this one was actually rather trivial. Next one looks rather tough. And so this is the one thing I really want to encourage you with a proof. If you look at an identity, is I have no idea where to begin. Like that looks nowhere near like they should be the same or they're equal. It's just like with that turning from math to ball. Just take one step at a time, and with each step that we take, hopefully we do get something that's going to closer to looking to proving that both sides are the same. So always start with left side, right side. So left side is cosecant of theta times 1 plus sine of theta. And the right side is 1 plus cosecant of theta. So another thing that is a hint for all trig identities is any time that we have a reciprocal identity, so a reciprocal trig ratio, we want to convert that to the primary. Okay, so really at the end, we're just dealing with sine and cosine, not with tangent and not with the reciprocals. So in this case, I'm going to do that for both sides. So cosecant is really 1 over sine of theta. And then this side, I'm going to do the same thing. So this is going to be 1 over sine of theta times 1 plus sine of theta. Now we're just going to use distribute this. So 1 over sine of theta. So it's going to be 1 over sine of theta plus, well, 1 over sine of theta plus sine of theta is sine of theta over sine of theta. So in this case, we don't need to add them. We could, But again, I'm looking at sort of the hint on the right side. What's my final target? I have two things that are being added together, two separate fractions. So I want to keep that. You can kind of see I'm close. I got one sine over theta here, I got one over sine of theta here. So here, we just turns out that we just simplify sine of theta over sine of theta. This happens to be 1. So there's going to be 1 plus 1 over sine of theta. And there we have left side, right side is the same. So that is proven. All right. So another proof. So here we get, we have sine. So basically we take sine, cosine, and tangent of angle, multiply it all together. And what we're saying is that this is really the same thing as 1 minus cos squared of theta. Right? So left side, right side. So right side is 1 minus cos squared of theta. Left side is sine of theta times cos of theta times tan of theta. So again, we want to, maybe a very first step is we see that tan, and we want to convert that to sine over cos. So here is going to be sine of theta over cos of theta. And so we multiply all this across. We're going to have sine times sine, so it's going to be a sine square of theta. And then we're going to have cos over cos. So really that cancels out. But I'll write it out anyways, to show that I'm multiplying out all the fractions, and eventually that cancels out. So I just get sine squared of theta. But back to my Pythagorean identity, we said that, well, sine squared theta is really 1 minus cos squared theta. And we kind of hinted that we're going to need to convert a sine to a cosine, because on the right-hand side, there is no sine. But on the left-hand side, we have a sine squared. So we're looking for, how do we convert a sine? Is there a way we convert the sine to a cos? Well, in this case, happy sine squared theta. So we know, and the identity says that, well, that's the same as 1 minus cos squared theta. So that one is proven. The next one, prove that cos of theta plus 1 over sine of theta is equal to 1 minus sine of theta over cos of theta for all angles between 0 and 360. Wow, this one looks like a doozy. Like, how do I get? Because here we got cos as a numerator and sine as a denominator on the left-hand side. On the vice versa, we got sine in the numerator, cos in the denominator. So this one looks really tricky. Like, how do we even manage this? So this one's going to require a trick, an algebraic trick. And I can't remember if I showed you guys this before. Probably not, because we didn't have to rationalize the denominator. So this is actually useful when we have to rationalize the denominator. So this is a trick what we call multiplying something by conjugate. So what do we mean by conjugate? So if we have a polynomial, so let's say a binomial, a plus b, well, the conjugate is really going to be, I'm going to write this in red, a, so we start to say, but minus b. So in other words, the sign of the second term changes. So why is multiplying by the conjugate interesting? Well, because really what's going to happen is we're going to get the difference of squares. So here we get a times a, which is a squared. Well, here we get plus ab. Then we get a minus ab, and then finally a minus b squared. So the a plus ab minus ab cancel out, and we get a squared minus b squared. So here we're going to get really a difference of squares. And the reason why we want to conjugate is we don't want that middle term ab. We just want the squares. And if we remember Pythagorean identity, what that dealt was sine squared and cos squared. So notice that here we don't have sine squared and cos squared, but we could sort of introduce it by multiplying by the conjugate. So in this case, what's the conjugate of 1 plus sine of theta? Well, that's going to be 1 minus sine of theta. So we want the next step, maybe we'll write it out as a whole, is I want to multiply by the conjugate. So that's why I'm focusing on the denominator. I want to multiply by 1 minus sine of theta. but we have to do that to the numerator as well. In other words, we were multiplying by 1, but we're multiplying by 1 minus sine of theta over 1 minus sine of theta. So in this case, we're going to get, well, cos of theta times 1 minus sine of theta. And the denominator, we're going to get 1 minus sine squared theta. Okay, so this is the power multiplied by the conjugate to get 1 squared, which is 1, and then really minus, and then sine times sine is sine squared theta. Well, why would we want to do that? Well, now we know that 1 minus sine squared theta, so we'll go back to Pythagorean identity again. This is going to be cos squared of theta. So here we get cos 1 minus sine of theta, so the numerator doesn't change. But we're going to change 1 minus sine squared theta to be cos squared theta. So remember, cos squared theta is just cos times cos. Oops, I forgot to fade it up here. So here it actually reduces this, and I get 1 minus sine of theta all over cos of theta. And lo and behold, that's what we have on the right-hand side. So we've just proven that. Okay, so that was kind of tricky. Well, not kind of tricky, really tricky, until we sort of see and get looking for something where really if we could multiply by the conjugate, that will get us a sine squared or a cos squared. And maybe that's something that we need to do. Remember, so we need to sort of convert sines to cosine. So we sort of hinted that we might need to do something like that, since the denominator of the left-hand side had sine, and the new denominator of the right-hand side had cos. So how do we sort of convert a sine to a cos? Well, chances are we're going to rely on the Pythagorean identity. The next proof, we're going to prove that 1 plus cot squared of theta is equal to cosecant squared of theta. So we're going to do left-hand side and right-hand side. So we're going to shortcut this one a little bit. When I say shortcut it, we're just going to, so one of the things that I said was we want to convert all the reciprocal trig ratios to the primary, and also convert all the tans to sine over cos. So we'll do the right-hand side first. Well, cosecant is really going to be 1 over sine squared theta. Well, the right-hand side, we convert cotangent to be 1 over tangent, and then reciprocate that. So just remember that cotangent of theta is, well, if tan of theta is sine over cos, well, cotangent of theta is going to be cos over sine. So we just convert that right away to be 1 plus cos squared theta over sine squared theta. All right, so we could have did in multiple steps. We could avert cotangent squared to be 1 over tan squared theta, and then be 1 over sine squared plus cos squared, and reciprocate that, we would have got this. So this is a little bit of shortcut, just going back to sort of the definition of cotangent is, now we're going to see sine over cos over sine. And we're just going to plug that right in directly. Well, here again, remember I said we have a fraction. We could always add two fractions together. Here's a hint on why we need to do that. Well, on the right-hand side, we just have a single fraction. So we need to combine these. We need to add these. So in order to add them, we need a common denominator. So this is why you always add two fractions together. You can always find a common denominator. So in this case, because this is really 1 over 1, our common denominator is actually sine squared theta. So that fraction doesn't change, but the 1 changes to a sine squared theta over sine squared theta. Now we can add those two. So we can get sine squared theta plus cos squared theta all over sine squared theta. Oh, and look at that. We have our Pythagorean identity there. This one turns out to be really easy. Sine squared plus cos squared, well, that just turns into 1 over sine squared theta, which just happens to be our right-hand side. So this was our first example where we really applied the Pythagorean identity in terms of getting sine squared plus cos squared, having those two added together, and they sort of all kind of simplify to just 1. I was going to say disappear, but things don't disappear. It just simplifies to 1. This next proof, so we have cosecant squared Theta times tan squared theta minus 1 is equal to tan squared of theta. So that's a mouthful. So let's write this all out. So left-hand side, right-hand side. So right-hand side, we'll just start off with tan squared theta. And again, we'll replace the tan squared with sine squared theta over cos squared theta. On the left-hand side, this is a little bit long. So here we get the cosecant square theta times the tan squared of theta minus 1. So how are we sort of going through and do this? So again, we take cosecant and change it to the primary trig ratio. So cosecant, that's going to be 1 over sine squared theta. And again, the definition or the quotient identity for tan squared theta, we could convert that to be sine squared theta over cos squared theta minus 1. So this actually is going to work out nicely because we got sine squared on the numerator and the denominator, so they cancel out. So we really got 1 over cos squared theta. So that's what that fraction is when we multiply it out, minus 1. So again, as a hint, we could always add and subtract fractions. So here we have a common denominator of cos squared theta. So it's going to be 1 over cos squared theta minus cos squared theta over cos squared theta. And then we're going to have 1 minus cos squared theta as my numerator, and then cos squared theta as my denominator. And again, going back to Pythagorean identity, this is one of the corollaries off of that. 1 minus cos squared theta, that's the same thing as sine squared theta. So we got sine squared theta over cos squared theta, what happens to be on the right-hand side. So we are done with that proof. All right. So I'm going to kind of go through these quick, only because we're kind of a little bit for time, but hopefully kind of seeing some of the strategies, some of the things that I'm doing. One of the things is, again, changing the tans to sine over cos, changing the reciprocals, and just really a lot of algebra that I'm applying. So another one that we have here is we're going to have tan of theta is equal to a whack of mess on the right-hand side. Sine of theta plus sine squared of theta over cos of theta 1 plus sine of theta. All that is really the same as tan of theta. Well, how can we prove that? Well, left-hand side, get the right-hand side. Should have set up all these grids ahead of time, but anyways, tan of theta is on the left, so I'm going to convert that right away to sine of theta over cos of theta. So really you can see the bulk of the work we're going to be doing on the right-hand side. So we got sine of theta plus sine squared theta all over cos of theta and 1 plus sine of theta times 1 plus sine of theta. So that's a big mess. Well, another trick that we can see is that, well, maybe we could do some factoring. Looks weird. How can I factor this? Because there's no x and y's and stuff like that. But there is a sine and sine squared. Okay, so one way that we could kind of look at this, if we let x equal sine of theta, a numerator looks like x plus x squared. So if we factor out an x, we're going to get x. Oh, that was slow. We're going to get x times 1 plus x. So we could actually factor things out here. So that's what we're actually going to do with our numerator, is we're going to factor out the sine of theta. So we're left with 1 plus sine of theta all over cos of theta times 1 plus sine of theta. So that actually worked out really nice when we factor that out, because we got 1 plus sine of theta on both numerator and denominator. That cancels out. And oh, that didn't turn out so bad, because we're left with sine of theta over cos of theta, and we're done. So here, one factoring that we did and reducing got us to the final proof of the identity. Okay, so while it looked tricky, the key there was seeing that I could factor out a sine of theta, and when I factor that out, I kind of see that hopefully you can kind of see that I'm left with 1 plus sine of theta when I factor that out. That is one of the factors, and therefore it reduces. Okay, this next one is a bit tricky. Only because we're going to go against one of the rules that I just said. And that's converting the tans to sine over cos. On this one, we actually want to kind of leave it a little bit. And here's why. Here I got 2 tan of theta. And here I got a binomial squared. So we're actually going to, first step on the left-hand side is we're actually going to square that. So let me write this down. Left-hand side is going to be 1 minus tan of theta, all quantity squared. Right-hand side is secant squared of theta minus 2 tan of theta. So I will convert the reciprocal of secant squared theta. That's going to be 1 over cos squared theta minus 2 tan of theta. Now the reason I could kind of see that I want to leave this tan alone is because on this side, when I expand my binomial, so it's really 1 minus tan of theta times 1 minus tan of theta, that's going to be 1 minus 2 tan of theta plus tan squared theta. All right, so remember how we multiply a binomial out. So again, we'll put something like 1 minus x quantity squared. We squared that 1, the first term of the binomial. Then we take the 2 terms, multiply together, and then multiply by 2. So that's going to be minus 2x. And then finally, we square the last term. That's going to be x squared. All right, so we're kind of doing that instead of x. We got tan. And from here, I can see, oh, I got negative 2 tan theta here on the left side. And now I have a negative 2 tan theta on the right side. So that's something that I want to try to leave alone now. And maybe somehow I could get the 1 plus tan squared of theta to be 1 over cos squared theta. So let's go off and start looking at that. So I'm going to rearrange this a little bit. So I'm going to get 1 plus tan squared theta minus 2 tan theta. So this is a different order. And now I do want to convert the tan squared theta to be sine squared theta over cos squared theta minus 2 tan theta. So hopefully you're recognizing as I go along through all these proofs, I'm just taking one small step, one small conversion that I could do, just like we had in that word problem, right? One letter, thinking one letter at a time. In this case, was one change to either left-hand side or right-hand side that's still true that I can make as we go along. So now I could add these two fractions. So again, the common denominator here is going to be cos squared theta. So you have cos squared theta over cos squared theta plus sine squared theta over cos squared theta minus 2 tan of theta. And finally, we're almost there. We can see that once we add that, we're going to get sine squared theta plus cos squared theta all over cos squared theta minus 2 tan theta. And finally, one last step is that numerator, sine squared plus cos squared. Well, from Pythagorean identity, that's just going to be equal to 1. So you get 1 over cos squared theta minus 2 tan of theta. And that happens to be what is on the right-hand side as well. All right, so that one was a little bit long, a little bit tricky, only because in some sense I did want to keep that tan, only because, and this is why I love about proofs in some sense, I'm given what I'm shooting for. I don't have to guess. I'm given it. I see that there's a negative 2 tan theta over there. Seeing that I have this over here, I do want to kind of keep that. Don't want to make work for myself. And eventually, we got there, and minus 2 tan theta was left alone. So here's the homework. Again, the thing about proofs is we did some practice. This is going to be practice, getting a hang of things. Maybe I'll summarize a little bit on some of the hints or tips that we want to use. So here, let me just create a new page. So one of the things that we want to look for is we want to convert all my tans to sine over cos. And really dealing with the reciprocal as well, to convert all my cotangents to be cos of theta over sine of theta. So another thing that we did was convert all reciprocal trig ratios to the primary, trig ratio, not ration, ratio. So here we're saying that we want cosecant of theta converts to 1 over sine of theta, and secant of theta converts to 1 over cos of theta. Okay, so just even those two simple steps, that's a step closer. That's a step closer. Another trick that we learned was we could factor. So look for opportunities to factor. So we could factor something out, and this is when we factor. Again, this is how we maybe simplify one side or the other by factoring. Maybe we could reduce. Another trick that or another tip that we could use is maybe multiply by the conjugate. Okay, so again, this is really useful when we have something like 1 minus sine of theta, or 1 minus cos of theta, or 1 plus sine of theta. So there we want to multiply by the conjugate, because there we just got sine or cos by itself, but then we're going to sort of turn that into a 1 minus sine squared of theta, or 1 minus cos squared of theta. So from there we go from either sine or cosine to the other one. Okay, so that's usually sometimes done by multiplying by the conjugate. As we do these, I'm sure we're going to discover other things. Oh, the last thing, that should be, that's what I remember, should have been number 3. So let me change this around. So really the top 3 are the most fundamental things. These last 2 I mentioned are sort of like little offshoots, little different things to kind of look for, but maybe not always applicable. But the third thing I forgot to mention is that we can always add 2 fractions, add or subtract 2 fractions. Okay, even though it looks like we can't because the denominators are different, we always come up with that common denominator, even just by multiplying the 2 denominators together. But we could always add or subtract 2 fractions. So usually a hint that we might need to do something like that is when we have sort of 2 terms on one side of the equation sign and only 1 term on the other side. So of course we have to add those 2 together somehow, and hopefully they could simplify into what we have on the other side. Okay, so there's a little bit of summary on some of the things that we can do to look for when we go off and prove identities.